So again, I start with a couple of slides. And the questions we will be answering is, what is an index anyway? What is it again? Why support those indexes? What are the right abstractions? What are the right interfaces, APIs? What should be the right interfaces? And how to get started when developing a database store. Again, in this lecture, when I implemented MVCC, I did not worry about indexes because I knew I don't have to do this. I can do a working store. I can write all my tests. I can implement all functionality without any index, without any data structure speeding up my computation. I can do that later. It's an orthogonal. It's a separate concern, and that's why I didn't do it. But now, when you look at the implementations of what we do, and maybe a great motivation for that would be, I guess, if you look at the store. So by the way, I refactored this a bit. So the code keeps on growing. We work on that almost every day now. And if you look at the hierarchy of the code here, so what happened here, previously there was a stores.py. I now broke it up into directory, and now I have for each store a separate file. So we have this first store, this version key value store we started with. Then we had this MVCC store, which I renamed to transactional key value store at some point. And now there's an indexed MVCC store. But when you look at what we looked at so far, there is this read objects iterable method that's basically used whenever you read something from the store. Yeah, so you have a where clause, some condition, some predicate, saying, okay, this is the stuff I want to read. And then you have something really, really bad, and that is this loop saying, okay, just give me whatever you have. This is basically meaning whatever data you have stored in your store, I'm going to loop over that. Yeah, again, that's nice for a toy example, but not for a real database store, because it's insane. Yeah? That for a single query, you read all of your store. Yeah? That's super, super expensive, but it does the job. Yeah? It's functionally correct. But now I want to go in a world where I don't have to do this, where I do something smarter than that, where I ideally only read the stuff that's relevant, where I only perform I/O operations, read it from SSD or from memory, only those objects that are relevant to my query, without reading all of it and filtering it. In this world, I would read everything from main memory or SSD or however the memory is backed, and then run it through this function, blah, 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 blah. Yeah, so that's not efficient. Yeah? That's not going to scale. So how do we go into a world where we don't have to worry about that? Okay. But first let's clarify. So what is an index anyway? And if you pull from main now, from the code, you will see that there are a couple of interfaces. And one is the index interface. We'll look at that in a moment. But conceptually, it's just a mapping from a key to a set of values. So in the more general sense, a single value. Yeah? Maybe I think I should fix that to say to a value. The set might confuse you because we introduce that later. To a value. A key is mapped to a value. Yeah, that means, okay, you have two methods to maintain such an index. You put a key and the value as parameter, and that adds a mapping, saying, okay, this key 42 maps to value Jens, or something like that. And you can also delete such a mapping. You can say, okay, this mapping 42 to Jens should now be removed from the index. And if you look at our implementation, you see it in interfaces. So that's a directory for all the interfaces. There's indexing subdirectory, there's an index, and that is the API for that. And here you see exactly that. So there's a put method allowing you to add a mapping to the index. There's a delete method allowing you to delete that from the index. Why is there a value in the delete method? And not just a key. Yeah?
Because one key
Right, a key may map to multiple values, and that's why I have to put it here. If it were only a key, then and I would call delete with a key, all the values associated with that key would be removed. I don't want to have that. So I want to have indexes that support these kind of mappings, that it maps to a set of values. Right, and the other is all about inserting data. For instance, a bulk load method, meaning, okay, I insert multiple values at the same time. That's not implemented yet in our code base. A flush method allowing me to signal, hey, dear index, please write that data back to the storage medium, make it durable. If you need some functionality like that, I did the flush method. But that's all about it, yeah? So why is there no query method? So how do I get data out of this? That's it already. There's no query method. Fancy, isn't it? It's just inserting. It's like a device null. It's like a black hole. Data gets in, but I never get data out. There's no get method whatsoever in this interface. And why did I do it like that? Because I added it through a so-called mix-in. Mix-in is basically it's kind of a variant of multiple inheritance. It allows you to add individual methods to your class. Now that's what I'm doing here. So again, this is a mix-in. Again, it's abstract. And it has a get method allowing me to retrieve the value associated with that specific key. Yeah? And then I can define types that mix an index with a point query. So I could say something like that. A key value store, for instance, is an index that also has a point query interface. It also has a get method, and that's called a mix-in. So the main type is an index, so I don't change any of that property, but I'm mixing in another property into my type. It's called a mix-in in Python, but in fact it's multiple inheritance, so I have two parent classes, or two parent APIs I'm inheriting from. And with that you have a key value store. Yeah, so the key value store we used before. If you remember, we have a key value store with these versioned lists in MVCC. That's a key value store, right? And then we extended that to be transactional. Now I'm saying, an index is very similar to a key value store. The only thing that the key value store adds over an index is this point query mix-in. Yeah? Okay, so we have these methods. And yeah, point query here again spelled out on the slide. So what's a point query is a conjunctive query that retrieves all values where for each attribute queried the key is equal to a specific constant value. Yeah, sounds complicated. It's not complicated. It's something like that. If you say a equals 42, that's a point query. I have to fix a pen here somehow. That's better. Okay, so if you say a equals 42, that's a point query, because in the domain, whatever the domain is that a is backed with, probably an integer, I'm interested in one particular point from that domain. Point 42, one element from that domain I'm interested in. That's why it's called a point query. And you can do that per dimension. You can also say C equals 43. That's another point query. You can say A equals 43 and C equals 43. That's a two-dimensional point query. Yeah? But so whenever there's equals in those conditions, in all conditions, that's a point query. However, if one of the conditions is more like in this range, greater equal, smaller, smaller equal, whatnot, then that's not a point query anymore. There's also range queries. We'll get there later. For the moment, we're not interested in that. Just point queries. And basically, what a key value store does is it just extends an index in terms of software engineering. Yeah? It is an index adding support for point queries, aka mixing in this get interface allowing you to retrieve the associated value with a given key. Yeah? That's all we do in that interface. And now if you look at the architecture, now it gets really, really wild. I mean, it's cool when we did that and saw that and what the implications of such modeling actually are. So this is a slide I showed to you in slide set 3, I don't know, 2 weeks ago or something like that. That's our architecture. And we already saw, oh, there's a couple of key value stores, right? And yeah, and we have all of these different key value stores. We have this persistence layers, those are key value stores. I told you, yeah, file system, it's just mapping from key to value, you know, right? Or key object store, key from value, you know, and so forth and so forth. So we already had these key value stores. Now we learned that these key value stores are indexes. Those are indexes. Yeah, so we have an index here. Here, we have an index here, we have an index here. So the key value store we're using to store data is also an index, and then we extended it to be transactional. That's the MVCC store, that's also an index. So don't worry, I am now adding way more indexes. So now I'm saying, okay, we have to extend our MVCC store to support indexes. So I write a subclass, indexed MVCC store or indexed transactional store, which of course, if you follow the hierarchy down here, is an index. And this indexed MVCC store, if we blow up the slide a little bit to make room, and that's basically what I'm doing here, I just enlarge the layer a little bit, internally has indexes. Yeah, it's indexes all over the place. It's fantastic. You can express everything with indexes. And I mean, maybe why is that the case? So it's also in general Python programming, a dictionary is an index. Yeah, every dictionary use associates a key with a value or a bunch of values. That's an index. Come on, right? Yeah, and that's the reason actually why now in the code we have what you see here. So we have to leave interfaces. We have to go to indexes. So that's not the interfaces. That's the implementations. And now what I did here is I wrapped an existing Python dictionary with my API. Yeah, so I just showed to you this key value store API saying, okay, it's an index, which also has the point query mix in. And now I'm saying, okay, why not wrap the existing Python dictionary with my API? Yeah, then I already have an index. That's the easiest way to get an index in Python. You don't have to do any super duper magic to get an index structure. You just use the existing facilities of Python. No? And that's all what this stuff does. So I have it in 2 variants without duplicates, assuming that for each key there's only one value associated, and with duplicates, assuming that the key can be associated with multiple duplicates. Yeah? So there's a second implementation with duplicates that where this delete method actually makes sense, yeah? where you really want to associate 42 with multiple values. So 42 maps to a list of values. You see it here in the put method. When you put something there, you try to receive, do you know the set default method in Python? It's a placeholder for, okay, if this key already exists, get me the value from the dictionary, which is a list at all times here in this implementation, and append this value to that list. If it doesn't exist, so if you try to look up the key, if this key doesn't exist in that dictionary, then please put an empty list there, and that will be the new value associated with that key. And then on that list, you additionally append the value in any case. Yeah? So that's just a very short way. So when handling dictionaries, there's always this nasty case, yeah, it's either already there or it's not there, and if it's not there, I have to initialize it. If it's there, I don't, tra-la-la-la-la-la. This is a one-line on Python allowing you to do that very efficiently. Yeah? But programmatically, that's all. Well, there's no rocket science here. It's just wrapping. It's just saying, okay, whatever Python is providing, I'm wrapping it into my indexing interface. Yeah? And that allows me already in my store And now with that, I already have an index implementation. I have a working index. It's not just APIs. I have already a working index structure that I can use for my purposes. Okay. So what that means is, so the previous key value stores and aka indexes here are now as is, as before on the other slide, in the other slide set. I'm extending the transactional key value store to have indexing support. And this indexed store may contain indexes inside that store. Yeah, so I may declare an index. I may say, okay, create an index. It's a method to call create index. It's also what you will find in SQL. Yeah? It's part of the data definition statements. You can say create index or drop index in the SQL database. And then the system will create an index, exactly in the way as I will show it in a moment. What that implies is that you also have to keep track of the indexes in that store. So you somehow have to have a mapping, an index, again, that maps from whatever index name to the index instance or maps from properties to instances and names and stuff like that. Yeah? So I'm stopping here with making it more crazy. Yeah? So this catalog, again, is an index in the sense of my API. I didn't do this to not confuse you even more. So I could make a 0.6 here if I wanted, which is the catalog. Yeah, that's okay. You can do that. And I think we have an assignment along the lines of the catalog here when it comes to transactional properties, but that's something for the assignment sheet. Yeah? So many of those components are now basically indexes, and the question I can ask to you, maybe do it later. Maybe do that later. It gets easier then. No? So one thing, maybe we start with a little bit of code here. I think then you get easier into it. So basically, when you look at our database management system now, some changes I did is that the database system itself, previously it used to be an asset store. And now I have a new interface, an indexed asset store. And when you go there, you see that's an extension of the old asset store. What I'm adding is a couple of methods, create index and drop index. And I used simplified methods here. So it's an index name, it's an attribute I want to index from my data, and it's a certain type of operator that index should support. We are talking about point queries here, so the operator will be equals at all times. I don't write equals, equals, I write simply equals in the store. You will see in a moment in the tests. That's how you create an index. And then you drop the index, and then specify the name, and then the index should be removed. There's also another third method here, get suitable indexes, and that is useful for looking up data. If you have a where clause, it has a certain attribute, and now you want to know, hey, does my store have an appropriate index for this kind of attribute plus operation? Yeah, and this method can be used, and we will use this when we look at the query optimizer later on. Yeah, so we don't need it here. Today's focus is really, okay, now I have the indexes, how the heck do I integrate them into the store? And how, in particular, do I make sure that I maintain those indexes? So what does index maintenance mean? That means is you make sure that any insert, update, and delete to that transactional store is also reflected in the indexes. As you now have two options or more options to either loop again over all existing entries in the store, or you ask the index, well, that shouldn't make a difference, yeah, in terms of result. Whether you ask the index, whether you scan over all stuff, the results, that should be exactly the same. Yeah? So you have to make sure when updating the store and when deleting anything from the store that the indexes are kept in sync and you don't get different results. So that's very important. And this is called index maintenance. Yeah? So for instance, assume actually my wife recently had this proposal that we have a huge fridge with stuff, and it really gets confusing to find what's in there. So she had the idea, okay, I write down a list with the stuff we have in the store. Yeah? That's the index. Yeah? It's basically saying, okay, we have whatever, this kind of food in drawer number 3 and that kind of food in drawer number 4. So that means whenever you remove some food, you also have to keep track on that index page. Yeah? And if you insert food, you have to keep track on the also on the index page as well. Yeah? I think the list got out of sync quickly. Yeah? So it's really hard to maintain these things. You can do that in software, and that's what I'm going to teach you with today's class. Yeah? Okay, but also to watch out here, you see there's an opportunity for an end-to-end test ahead, of course. Yeah. So what is the end-to-end test when you do something like that? End-to-end unit test. We talked about that last time, I think. Yeah, someone else? Yeah?
Just change something in the transactional store and then do 2 reads, or basically we have some where clause and we actually want on the index or all indexes and want on the transactional
Right.
store.
Right, that's the perfect end-to-end test. You develop an index, you can always compare against the results of a full scan. Yeah, this is analogy we had last time was, okay, you implement a join algorithm, you can always compare it against cross product plus filter, yeah, the filtered cross product, that's equivalent to the join results. So you can directly compare the result sets. So it's super easy end-to-end test, super useful. Right. And with that, so let's start with the create index methods. So you will now see that in the, again, system stores, indexed MVCC, indexed transactional key value store. If you go here, you will see, this is now inheriting from transactional key value store, and it's implementing the indexed asset store interface, which contains create and drop index and get suitable indexes. So what do? I do the standard fluff of, I have a constructor and I reroute to the superclass constructor. In addition to that, I have to create these 2 dictionaries. They could be indexes in my APIs. As I said, I didn't do it, but I could do it. So these are dictionaries mapping from the index name to index properties. Yeah? You see it here in the type, that's the index catalog entry. And that keeps index properties and the actual index instance, which I require in my store to be a key value store. So it's not just an index in the sense I can put stuff into it. I can also at least call get on that. Otherwise, it doesn't make sense in the database system. I want to get data out of that. Yeah? That's why I use the key value store type here. And the index properties is just saying, okay, this index was created on this attribute, and it supports this type of operator. I need to keep track of that information for query processing later on. Later on, I want to query the store and say, hey, I have this where clause. Do you happen to have a suitable index for that? Yeah? And then the store should say, hey, I got one. Or it should say no. And if it says no, you as a user may say, okay, then I create the index. If you don't have it yet, I will create it now, and then you have it for the next round. So that's basically the kind of information you have to keep here. So you have this dictionary by name, so I can look up the index with a name. What's more suitable is that I can look it up by properties. Yeah? So I can say, okay, hey, this is my where clause, this is my attribute, this is the operator I want to support. Do you happen to have an index on that? And then it returns the name of the index here, and then you can use that in the other dictionary to get the actual index instance. Yeah? That's what we need for exploiting those indexes. So this read part, reading from the indexes, is not yet implemented in the store. It's really, you will see already when we now discuss updating, Yeah, it's not so easy because we have a version store underneath, and that requires some thinking to avoid pitfalls. Okay, so I have some helper methods here. We'll go into that later on. Maybe start with the easy ones here, create index. Yeah, saying, okay, please create an index on tra-la-la-la, and so forth and so forth. We do the standard checks. Is the name already existing? Then that's an error. Or if it's any operator that's other than equals, oh, sorry, I can't do that. So for the moment, the store only represents equality queries, point queries. Yeah, I also added a lot of, maybe you read back home through the documentation where I explain many things here. Yeah, here I add metadata to the catalog. And I have to create basically those entries for both dictionaries to keep track of the index I create. And then I bulk load the index. Bulk loading meaning, now really all items I already know about, all objects I already know about in my store now have to be known to the index. Yeah, so which basically means here I loop over all entries. Again, this is super expensive. I'm saying, okay, whatever items exist in my store, I have to make those items known to the index. And that's what I'm doing here. Yeah? So basically here I call index, underscore index object on this index I just created. That's the instance to the index I created. So here I create this Python dictionary. Yeah? The Python dictionary with duplicates. And what this method does is, for this given index on this attribute and this object ID, that is the version that should be indexed by the index. Yeah? So it's basically filling the index with all the data that's available in the store. Yeah? And you do that once when creating the index. Then when you drop the index, you do kind of the inverse, of course. Yeah? Do the checks. Do I even have an index with a name like that? Then you get the entry from your catalog, from your dictionaries, and then basically you remove those entries. Oopsie. Okay. Then, hey, what's wrong here? Hey, I didn't do anything. Then you remove these entries from your, where am I? Drop index here. You remove your entries from your catalog. Does anyone see a problem with that? So I'm removing the instance, the index from my catalog, from these two dictionaries. Is that enough, or should there be anything I should do in addition to that? You may raise your hand first, then it's okay.
Shouldn't you also like to remove the data itself?
Which data? Yeah? Which changes? Yeah, but I'm dropping it anyway, right? Okay, but that argument you could make in the create method as well, if I understand you correctly, right? So here, I mean, so I'm a Python dictionary, it's in main memory, there's no persistence anyway here implemented. So where's the persistence anyway? Changes to the index that you not made. No, the index is an additional structure on top of the store. Yeah, that's important here. So the store is a point of truth. The index does not replace any of that truth, so just an additional method allowing you to retrieve that data faster. So durability is kind of orthogonal in a way. Yeah, I mean, maybe you're alluding to you have changes in your index that weren't persisted yet, and then you may get in trouble and lose durability for some transactions, yeah? Yeah, every time we do this validation and commit, we go through the write sets, the tuple IDs, and we didn't talk about that yet too much because that can be done way more efficiently, but in practice you could flush every object ID, make sure that it is persisted. Yeah? That's not the big issue here. But one minor issue, maybe not these days anymore, but if it were persisted, if your index is a super duper big index that's also persisted on disk, maybe you want to clean up. Maybe you want to remove the stuff. Remove it from file or wherever you had it, or C++, you free the memory or something like that. Probably the destructor would be called automatically in C++, and in Python it's always, you never know. On a good day it's called, on a bad day it's not. So there should be a more explicit way of cleaning up the stuff when deleting an index. Okay. Yeah, maybe we start a little bit with update objects. We won't have too much time. We make one round and then we start with that next time. Again, the core idea is this is a wrapper to the underlying transactional store without the indexes. So you will see at some point, aha, I'm calling the super method, as is, with this weird super bracket notation in Python, calling the update object method from the super class. How I do this here is I get the existing work in progress entry if it exists. So there's actually the case where you have to be careful when maintaining the indexes, because the principal idea here is, well, it's versioned. I never have to remove anything from the index anyway. I never throw anything away in my index, in my store anyway. This is so cool because it just means when updating stuff, I append a new entry to my index. It makes life easier. That's what I thought when starting to implement it. But then I bumped into the trap that, hey, but Jens, wait, what if the same transaction creates multiple work in progress entries? Oh, you're updating in place. The work in progress entry is updated in place, which means now if I create a work in progress entry, put it into the index, and then I replace it by a new work in progress entry, oh, I better remove the old one. That's the only point in time, to my understanding, and also aborting a transaction is a second, where you really have to de-index something. You have to remove it from the index again. Other than that, it's just adding. Yeah? Again, in a real implementation, you would also discard old versions from the store. Yeah? These old committed versions no one reads anymore. Garbage collection or vacuum in Postgres. There again, you have to remove it from the indexes. That's not done here. We don't remove this stuff. But in principle, so what you get is, and you need this for that is, you get the existing work in progress entry. Yeah? So this can only exist if this transaction here sent a previous update or delete operation of some sort, any modifying operation. Then you call the actual update object, which will create a new work in progress entry. The committed list must be unchained. I just that's also something I highly recommend. Insert asserts wherever possible. Yeah? You can make the argument, yeah, it makes it slow. Oh, who cares? If you know, aha, that's a post condition, and I can write an assert for that, write down the assert. It makes debugging so much easier. Yeah. Now I get the new object version visible to this transaction ID. Yeah? So my private snapshot now updated by this transaction. Yeah, I could actually also get directly the work in progress entry at this point in time. That would be another variant of doing that. And then I maintain all indexes for this change. So this maintain indexes method, we enter there a bit more on next Wednesday, I would say, but basically it gets the object ID, an object to index, and an object to de-index. So if you specify none in any of these parameters, there is nothing to index or there's nothing to de-index, which also means here, and that's a trick, if you get the existing work in progress object, and that is none, that implies that no update was done by this transaction before on that object. Otherwise, you would have received an exception. So that would be none, and that means nothing has to be de-indexed here at this point in time. However, if you send an update before, there is an object being passed here, and that will be removed from the index. Yeah? Okay, so far so good. Take a look at the code. All of this is on main. We will continue there next week and then also look at other index structures. See you then. Thanks.